So, a confidence interval gives a range of plausible values for a population parameter. In this case, the true difference of two means. So we're looking at mu1 minus mu2, or x bar 1 minus x bar 2. 1 and 2 are simply just because you have two samples. You can make subscripts. These little numbers below are called subscripts. You can make them so they fit with whatever you're doing, so you can tell the difference between them, or you can label them however you want. The key with these is to think of, as you're going through this, what does the difference mean? What does a positive or negative difference tell us about this information? Okay, in a confidence interval for a difference of two means and or a hypothesis test for a difference of two means, you are you're looking to see which is better a lot of times. Which is better, which has more, or which has less. So you're doing a comparison. All right, so we're going to do a test on fertilizer. So to test if a new fertilizer is effective, 20 similar tomato plants were randomly assigned to be planted in either regular soil or soil with fertilizer. After 3 months, the total weight of the tomatoes from each plant was measured. These figures in pounds are below. Construct and interpret a 95% confidence interval for the difference in mean production for the two conditions. Does the interval give evidence that soil with fertilizer is more effective than regular soil for growing tomatoes? So we've got our data here, and just if you want to, I about dropped that. If you want to be able to follow along with the calculations and stuff on here, it would be a good idea for you to put your data in lists. So stat, edit, and I'm just going to put regular soil in the first list. And then fertilized soil in the other list. Okay. So then you can, you can do the test with us and do the normal probability plot. So if I calculate the means, if I go stat, calc, one variable stats, and I want to do it, my lists are in list 2 and 3. I have a calculator that the first list is deleted. I haven't put it back yet. So for the first one, so X bar for regular soil is 7.3. And the standard deviation for regular soil is 1.49. So then if I go stat, calc, one variable stats for the next list, I get that X bar for the fertilized soil, F, is equal to 9.9, and the standard deviation for the fertilized soil is 1.7. Oh, wrong, 7.9. It's always the S one that you should use. I just liked that one because it was short, but can't use it. So N for each of those is 10. So that's where the data is going to become, that's where the numbers are coming from down a little further. So we have a 4-step procedure for doing the confidence intervals. It's the same as it was before. So we're trying to estimate the true difference in the mean weight of tomatoes grown in regular soil and the mean weight of tomatoes grown in fertilized soil. So we're finding the mean of regular soil minus the mean of fertilized soil. That's the true mean we're looking for. Our best guess is this difference right here. If you take 7.3 minus 9.9, do you get negative 2.6? Could you do that on your calculator? Some of you are just spacing out. Okay. If you subtract those, do you get that negative 2.6? Now, what does the negative value tell us about the relation? Okay, go ahead, Mitchell.
Fertilized soil is more higher.
Of what? Very good. The fertilized soil made more tomatoes. That's what the negative difference tells us. Okay? If you're subtracting regular soil minus fertilized soil and you get a negative, that means the fertilized soil gave more tomatoes. That's what it means. So that's the kind of stuff you have to think about, especially for interpreting the stuff at the end when you interpret it in the context of the problem. So that's what we got for difference. But because of, and I talked about this in the first video if you watched it, this is not sampling variability, it's randomization variability because this is an experiment. So when you do an experiment, it's not sampling variability because you didn't select a sample, it's the way you put them into groups. So the question, what if I had put the plants, they got split up differently? That's the variability that could have caused this difference. So what we're going to do is calculate a 95% two-sample T interval for the mean difference. Okay, you say the confidence level, how many samples, what's your test statistic, and then what variables it's for. P, mu, now it's a difference of two means. So we have to check our conditions. Conditions for means, are they randomly assigned? Yes. And for experiments, it's really nice. There's only two conditions you have to check. Treatments are randomly assigned? Yep. And are they approximately normal? Now, if you would happen to forget and test that 10% or independence condition, that would be okay. It's not going to be a huge deal. It's better to check more conditions than not enough. So, approximately normal, well, I don't know. You just need to check the NPPs. So I'll just do the NPP for one if you go second stat plot. I want the last graph. And my data's in, I'm just going to do for the regular soil. If I graph it and hit zoom 9, does that look approximately linear? Yes. Okay, and it matches, that's where these came from. They just did the normal probability plot. So since they're both approximately linear, roughly linear, it's safe to assume that they come from normal populations. So now here's our confidence interval. This is the same formula I just wrote as I went over the homework. It's the difference of two means, plus and minus your T, and they usually put like a T star. It just means that's your critical value. The star means critical, and T. And then, so there's your formula. And then they plug the numbers in, mean 1, 7.3 minus 9.9, 2.262 if you look up. Well, basically you let your calculator do it for you. But if you wanted to get the correct, well, you can't unless you do the degrees of freedom. So we'll do this on the calculator. So if I want to type all this information into the calculator, you're going to go to Stat Tests. You still need to write down the formula or the formula with the numbers plugged in. The problem with this though is that could be a little different. Okay, because of the degrees of freedom. All right, so I'm going to do a T interval, two-sample T interval, and I actually have the data, and it's in list 2 and 3. Frequency is 1, 95, not pooled. Calculate. So this tells me that my confidence interval is the same. Now this is a little bit different, so negative 4.154 to negative 1.046. And the degrees of freedom is 17.437, and that's all they give you. So if you're going to use your calculator, the only things you're going to write down are this, degrees of freedom, and the interval the calculator gives you. Now, where did they come up with this 2.262? Well, they might have used inverse T, but you need to know the degrees of freedom. What would the degrees of freedom have been if we used the conservative 9? So the degrees of freedom would have been 9. So if you looked on your T table at 9 degrees of freedom for 95% confidence, that's where that 2.262 came. So for this, if you just use the conservative value, that's fine. But then don't use your calculator to calculate it. If you use the conservative degrees of freedom and put that T here, then you need to finish it off by hand. Yes?
How did you get the confidence interval to come up on the t-test?
I'm not doing a T-test.
Oh.
I did stat tests. I go down to the two-sample T interval.
Oh, okay, that makes sense.
It's interval.
Gotcha.
And it just says, note the degrees of freedom calculations are the same as for the two-sample T-test. The interval above is using the conservative degrees of freedom. So you may also use the test menu to calculate the more exact two-sample t-interval, but you should know how to do it by hand if necessary. For example, on a multiple choice question. Okay, so your final summary is I'm 95% confident that the interval from negative 4.7 to negative 0.93 captures the true difference in mean weight for tomatoes grown in regular soil and tomatoes grown in fertilized soil. Your conclusions will be a little clumsier, if I might say, because you have to talk about the difference. Now, since the interval of plausible values is entirely below 0, okay, if the difference is 0, if I would subtract these two averages and get 0, that means there is no difference between the two things. If the value is all negative, it means the second one is higher. If it's all positive, the first one is higher. Does that make sense? Just rules of subtraction. So for this problem, since it's entirely negative, that means the second one grows more tomatoes. So in other words, the fertilized soil does indeed grow more tomatoes, since our interval's all negative. Either way we did it, it was all negative. All right, so now we're going to walk through one on our own. All right, so in a recent study, Pediatrics 2004, I guess 10 years ago, investigated the effect of fast food consumption on other dietary variables. For a sample of 663 teens who reported that they did not eat fast food during a typical day, the mean caloric intake was 2,258 with a standard deviation of 1519. So I'm going to call this no fast food. So no N for no fast food. You can use whatever you want. You could use sample 1 and 2. It doesn't really matter. All right. So the second sample, N was 413 teens who reported that they did eat fast food. So I'm going to say F for fast food. And their mean caloric intake was 2,637 and a standard deviation of 1138. That's a huge standard deviation. Construct and interpret a 99% confidence interval for the true difference in mean caloric intake for these two types of teens. Okay, so first of all, I'm going to do kind of a shortened version here. Okay, so step 1, we're going to do a two-sample T interval at 95%, 99% for mu of, do you want to take not fast food minus fast food or do it the other way around?
No fast food.
Okay, so no fast food minus the mean of fast food. It doesn't matter how you do it. It makes no difference. You just have to be able to interpret it either way. So we're going to do a two-sample T interval for the mean difference in between caloric intake, kids who eat fast food and who don't eat fast food. All right, so now step 2, check our conditions. So condition 1, it was a random sample. Step 2, we're going to assume that both 663 and 413 are less than 10% of.
Do we have to?
Yep.
I thought
No,
we
we
just-
do. This is not an experiment. Okay, if it's an experiment, you
Oh, we don't
only have to. Yeah, if it's an experiment, you only have to check the random sample, and the large sample size. But here, since this isn't, we have to check all 3 conditions. So random sample is stated. Assume both 663 and 413 are less than 10% of all teens. And N is definitely greater than 30.